want to spend a few minutes sort of extending what we just saw in the course proper, let's say, and show you how you would start working with spanning trees in igraph. So I've made this little worksheet. It's going to be quite short, okay? I'm mindful of time on the one hand, and there's not a lot of things that I want to say anyway. What we're going to do is load igraph, as we have in the past, and I'm going to show you a few examples. So the first one is I'm going to make a full graph. If I call it a full graph, call it a complete graph. So I'm going to make a complete graph with 5 vertices, or maybe let's be a bit more ambitious and make 10 of them. So every vertex is connected to every other vertex. I have not imposed directionality, so the graph is undirected by default. And it is, of course, connected because it's a complete graph, so every vertex is connected to every other vertex. And so here I'm just computing the components and displaying the number, and you can see there's one connected component, which means that the graph is connected. And then I can just use this function, minimum spanning tree, which is going to give me the minimum spanning tree. So it's a little particular type of spanning tree. I'm not going to get into the details here. What it does is it tries to minimize some value. It sort of gives a bit more predictability in terms of what it does than just picking a random vertex and applying the algorithm we were talking about when I'm removing arcs or edges in this case. So this is a little bit more more organized, but the idea is still the same. I'm going to get a spanning tree, and let me plot it. So it's made a spanning tree, and we could go into the details as to why the graph looks like this in this case, but this is due to the fact that the graph is complete. Okay, but everything is in connection with everything else. Just to show you that the same thing works if we make the graph directed. So, okay, let me stick with 5 vertices this time, but here I'm imposing that the graph be connected. So I get this nice pentagram, essentially, where you can see that now I have arrows and it's connected, so every vertex is connected to every other vertex. So that means that I have arrows in both directions because now I am directed. And the same way, I've got a single component. So in this case, by default, now I'm in the directed case, and we will see that very soon. If I don't specify that I'm looking for what are called strong components that will make a course very soon, then by default components in the directed case look for weak components. And weak components are exactly what we were talking about in the course, where the direction of the arrow doesn't matter. So we can follow an arrow any direction, well, an arc in any direction. It doesn't have to be in the direction of the arrow. Okay, so once again, I'll compute the minimum spanning tree, and you can see that this one is directed, and I have no loops. So like it's a spanning tree or it's a tree, so it cannot have loops. And here you can see that the arrows are now one directional, and this is what we get as a spanning tree for this. The last thing I want to spend a couple of minutes about is the fact that we can make trees as well from the beginning. So we can say, okay, make me a tree. And so there's that function. And so here I'm not defining g equals make tree of this. I'm just plotting the result of making a tree. I'm not going to go into the details. If you want to know what the function does, well, I recommend that you take a look at the help of igraph to see what those parameters mean. In a sense, those parameters talk about the number of vertices and the sort of number of branching that you're going to see in most cases. You can see that here I have two branches, two branches, two branches, and so on. And you can, again, make a tree that's either directed, such as this one that I've made, or undirected, and so you get something resembling this. Another thing, another type of tree, a much simpler type of tree, is what we call the star graph. And the star graph can also be directed or undirected. And it's a tree because this is exactly satisfying the definition of a tree. There's no cycle, everything is connected. And so that's it. That's all I wanted to show you. Perhaps, since I do have a couple of minutes left, maybe let me make something a little bit more complicated. So make, which one do I want to do? Or maybe let's do a sample instead. Just by curiosity, let's do a sample GNP that has to be Erdős-Renyi graph, I believe. So if I say 100 and 0.1 equals this, it looks like it's running. Plot G. I just want to show you a situation where things are much more complicated. Maybe I need a smaller value. Okay, this was too small. That second number is the probability that a given arc, or yeah, maybe I should make it a given arc or edge exists. So this is the undirected case. Okay, so here it's made a graph like this, and let's get the minimum spanning tree. So we call it spanning tree. The function can also be called with MST. And let me, sorry, I forgot, plot spanning tree. There it is. And so here we're in a case where a lot of those, of course, I should be able, I should, or maybe let me make a much smaller graph so that we can see things a bit more detail. Let's take a slightly higher probability of connection. It's tenuous, right? It goes from almost no connection to... Okay, so here I have, what I should get is a forest. Actually, most of those, this is a little too... Okay, this is a bit better because there are cycles and there are isolated components. And so what we're going to get, so that first plot is the graph that I created. You can see that here I have a cycle. Here I have components. And so what it's doing now, it's transformed this one into a tree. And this is what has happened here. Okay. These are automatically trees, and those that are isolated here remain isolated. Okay. We could play with this for a while. Probably wouldn't get much further. Let's see if I make it a bit more connected. Yes, it's a little bit. And once again, so these are already trees. So, and this is This one is a bit more complicated. You can see there's a certain number of cycles here, but these cycles have been removed and I have a minimum, well, I have a spanning tree instead here. And that's it for the beginning of spanning trees.